Hello students, welcome to this class of transport phenomena. In this class we will discuss about the shell energy balance in case of composite wall. We already discussed the shell energy balance in case of nuclear heat source, in case of electrical heat source, in case of that viscous heat source. Now in this case we have discussed about the heat conduction through composite wall and we will study about the energy balance in this lecture. First of all, we have to remember the shell energy balance equation, which states that for a steady state condition, the rate of energy in and out in case of molecular as well as convective transport plus the rate of work done on the system by molecular transport minus rate of work done by the system by molecular transport plus rate of work done on the system by external force plus rate of energy production is equal to 0. Since by name it is showing that it is a composite wall, so it is made of a different materials which having a different thermal conductivity and the thermal properties. As shown in the figure, it is found that it is made of three substances, substance 1, substance 2 and substance 3. The substance 1 having a thermal conductivity denoted by K1, substance 2 have a thermal conductivity denoted by K2 and substance 3 is thermal conductivity denoted by the K3. These substances are at a particular distance and they are clubbed to each other by a ball. The distance between the two thickness is denoted by x0 and x1, x1 and x2 and x2 and x3. The composite wall is having a width of capital W, the height is denoted by capital H, and there is a two fluid which are available at both the surfaces which having the temperature Ta, which is denoted on the left hand side, which is as a fluid A, and the temperature Tb on the right hand side of a fluid B. There is a elementary section which we take place in the section 1, which is denoted by delta x. The flux which in and out is taken by the qx, which is it is a x direction flux. The temperature at the each wall of the composite wall is denoted by T0, T1, T2, T3. The fluid which are showing here having a temperature Ta, the fluid B which having a temperature Tb. The thing which already discussed in the last slide is already present in this manner, and in this case we have also one substitution is there. The temperature Ta, which is the temperature of a fluid A, is always greater than temperature V, that is a fluid B temperature. So the heat flux is flowing from the direction to the left to the right. Basically the fluid is flow, so there is a heat conduction as well as heat convection taking place. In the next slide, there are the following assumptions taking place in the heat conduction through composite wall. First one is the steady state condition. Second one, the thermal conductivity of the slabs K1, K2 and K3 are constant and it does not change with respect to temperature. The third assumption is there the heat flow is taking place in the only in one direction, that is in the x direction. We are not considering here that the heat flux taking place or heat flow taking place in the y direction as well as in the z direction. The next assumption is that heat transfer at the boundaries, that is at x is equal to x0 and x is equal to x3, is given by Newton's law of cooling, because the at the surface at x is equal to x0 and at the surface at x is equal to x3 there is a fluid. So the Newton's law of cooling is valid because there is a mode of heat transfer which taking place is the convective mode. So with respect to that, the Newton's law of cooling, there is a heat transfer coefficient which is denoted by H0 and H3, which are denoted the heat transfer coefficient at the surface at X0, and H3 is the heat transfer coefficient for the surface X3. The From the above equation, we have to now calculate the energy balance equation using the heat flux equation in the x direction. Let Qx is the heat flux flowing in the x direction. Let us consider the shell balance at the surface x and at the surface x plus delta x. As shown in the figure, we have to consider the shell balance in these two positions, that is in the x position and in the x plus delta x. The flux is input at the position x and the flux out is taking place at the x plus delta x. Now, since there is no heat generation term because it is only flowing of flux from the fluid A to the fluid B due to temperature difference, so there is no external heat generation sources. Therefore, the energy balance equation is given by rate of heat in at surface X minus rate of heat out at the surface X plus delta X is equal to 0, because there is no work done on the system, there is no work done by the system, there is no work done by the external force, and there is no rate of heat of generation by the external sources. So the total energy balance is only rate of heat in and rate of heat out, which is equal, denoted by the molecular transport. In the region 1, that is in the surface or in the substance 1, we have to consider that the flux flowing is in the x direction, so we have to convert the flux into flow by multiplying the cross sectional area, as the flow direction taking place in the x direction, so the cross sectional area is denoted by W into H, because it is a perpendicular area in the direction of the flux. So the Qx is the flux of x direction at surface x, multiply the cross section area, minus Qx at the surface x plus delta x, multiply the cross section area W into H, is equal to 0. Now the equation is divided by a volume, that is WH into delta x, and delta x tends to limit to 0. So by L'Hospital, we have just generated an expression which is showing that limit delta x tends to 0, Qx at x minus Qx at x plus delta x upon delta x is equal to 0, which is denoted in equation number 3. On by basically by L'Hospital, it is converted to a differential equation which is denoted as dqx over dx is equal to 0, which is denoted in equation number 4. Now on integration, we get a flux constant value, because qx is depend on x, and on integration the 0 is become a constant and it is denoted by q naught, and the q naught is a flux which is at surface x naught, because we already studied in the heat transfer that the direction of the flux at all the surfaces of the heat transfer is basically constant and it is having a same value, so it is denoted by q naught. So the equation is valid for all the three slabs, that is substance 1, substance 2 and substance 3. So in cases the flux is equal to constant, that is qx is equal to q naught, which is denoted in equation number 6. Now applying the Fourier's law for generating the temperature profile, we have to apply the Fourier's law of heat conduction in all the region 1, region 2 and region 3. As in region 1, Qx is equal to Q naught, it is equal to minus K1, because the thermal conductivity at the substance 1 is K1 minus K1 dt over dx, which is denoted in equation number 7. For region 2, Q naught is equal to minus K2 dt over dx, because the thermal conductivity of a substance 2 is denoted by K2. For region 3, that is for substance 3, Q naught is equal to minus K3, which is denoted as minus K3 dt over dx, and the K3 is the thermal conductivity of the substance 3, and it is denoted by equation number 8 and at 9 respectively. Now integrating each equation, we get the each temperature profile. Now from the figure, it is recognized that for the substance 1, the temperature range is started from T0 to T1. T0 is the temperature is maintained at x surface x0, and T1 is the temperature at the surface x1. For the substance 2, the x1 temperature is maintained as per for at x1 temperature is T1 is maintained, and at surface x2 T2 is maintained. And for the substance 3, at surface x3 T3 the temperature is available. Now on integrating, first of all we have integrating in case of region wise. So in case of region, first of all we have to just maintain the equation, or we have to just simplify the equation by substituting the temperature term in one side and other terms in the other side. So dt is equal having here, and the q naught upon k1, which are all two terms are constant, so the dependent term is only dx, and we have to just put a limit with respect to the direction. So at surface at x is equal to x naught, the temperature is T naught. For surface x1, the temperature is T1. So the by integrating, we get T naught minus T1 is equal to Q naught minus upon Q1, we get T x1 minus x naught. For region 2, it is T1 minus T2, which is equal to Q naught upon K2, x2 minus x1. And for the region 3, T2 minus T3 is equal to Q naught upon K3, x3 minus x2. So these three equations, that is equation number 10, equation number 11 and equation number 12, is showing the temperature difference in the solid, basically in the slab, which is taking place with the help of Fourier's law of conduction. Now we already discussed, or we already tell that in the previous slides, that for the reason having a fluid A and the fluid B, there is a mode of heat transfer is convection mode, so we have to deal with the Newton's law of cooling is there. So we have to apply the Newton's law of cooling at the surface at x is equal to x naught and x is equal to x3. We will get, so at surface at x is equal to x naught, q naught is equal to h naught Ta minus T naught. As is shown in figure, the temperature difference is there. Ta is the temperature of the fluid and the T naught is the surface temperature, which is for a fluid A case. So the Newton's law of cooling is valid in this case, and we have to just get a q is equal to h naught into delta T. Delta T is here is Ta minus T naught. So from that we get a temperature profile for in case of fluid A, that is Ta minus T naught is equal to Q naught upon H naught, which is denoted by equation number 13. Similarly, at surface x is equal to x3, we get a temperature profile that is T3 minus Tv, which is equal to Q naught upon H3. As already shown in figure, the fluid V, the temperature at the surface is T3 and the fluid at temperature Tv. So the temperature difference between taking place T3 minus Tv. And it is denoted in equation number 14, where H naught and H3 we already discussed that heat transfer coefficient of fluid A and fluid B respectively. Now the above equations, that is equation number 10, 11, 12, 13 and 14, we have add and we get find out that the all temperature terms, that is T1, T0, T2, T2, T3, all terms are nullified and only the terms which are available is here Ta minus Tb, that is the temperature of the fluid A minus the temperature of the fluid B. And we already take out the Q naught as a constant term and the rest term which is denoted as 1 upon H naught plus x1 minus x naught upon k1 plus x2 minus x1 upon k2 plus x3 minus x2 upon k3 plus 1 upon h3 club in the one term. And this one term is basically in the next slide we will discuss about it. It is a overall heat transfer coefficient. So from this we get a value of a Q naught which is equal to Ta minus Tv upon the term, that is 1 upon h naught plus 1 upon h3 summation I is equal to 1 to 3 xi minus 1 upon ki. This is basically a general equation which showing the summation of the heat transfer coefficient as well as the thermal conductivity terms. So equation number 15 can be written in either in term of heat flux, that is heat flux basically it is amount of energy per unit area per unit time, or in the form of heat flow, that is amount of energy per unit time. Now in the next slide we also discuss about the overall heat transfer coefficient, which is denoted by a capital U. As the heat transfer coefficient is there denoted by capital U, it is an overall heat transfer coefficient, so it contain the all the thermal parameters like conductivity, convection, which are the parameters available in the different cases. So Q naught is equal to U into Ta minus Tb, which is denoted in equation number 17, or it is sometimes that, so it is a flux equation. If we convert it into a flow equation, we have to multiply by the area, which is a cross section area. So U multiply by W into H, because it is in the direction of the flow. The cross section area is W into H. So Q is equal to U into area, that is W into H, Ta minus Tv, which is equation in 18. Now comparing equation number 17 and 18, we get that 1 upon U is equal to 1 upon U, sorry, in comparing equation number 17 as well as equation number 16, we get 1 upon U is equal to 1 upon H naught plus 1 upon H3, that is summation I is equal to 1 to 3 xi minus 1 upon ki, which is denoted in equation number 19. So from the above two equations, that is equation number 17 and equation 16, we get the overall heat transfer coefficient term, and we analyze the overall heat transfer coefficient take place in the composite ball, and it is denoted by a 3 slabs. But in case if it is available of n number of slabs, then we have equation that changes only by the term that 1 upon U is equal to 1 upon H naught plus 1 upon Hn plus summation I is equal to 1 to n, because n is a number of slabs which are places there, xi minus 1 upon ki, which is equation number 20. That is the overall heat transfer coefficient in case of composite having n number of slabs available. Thank you for this reference. For this, we have to go for a reference that what is Stewart and Lightfoot of transport phenomena. Thank you. And if you have any query, please ask me in the comment box, or you can ask in any time. Thank you very much.